Welcome to video 2 in Unit 6, where we'll continue to discuss reduction reactions of carbonyls. In the first video in the series, we looked at reactions where carbonyl-containing compounds can, in principle, be reduced with a mixture of sodium borohydride and some kind of alcoholic solvent or water. But we also established that esters do not react under these conditions because the reaction is too slow. One way we could rationalize that is we have an ester which we know is not a particularly electrophilic carbonyl. So we'll say this is a weak electrophile. And this result, that the reaction is too slow, tells me something about the nucleophilicity of the hydrogens in borohydride. These are probably only kind of moderately or weakly nucleophilic. So they're only going to react with our most electrophilic kinds of carbonyls, things like aldehydes or ketones, for instance. So these are going to be weak-ish nucleophile, and that leads to our rate issue. If we wanted to be able to reduce esters, we would need to solve this problem using 3 different kinds of strategies, or maybe some mixture, right? We could try to change the electrophilicity of the ester, we could change the nucleophilicity of our reducing agent, or we could try to use some kind of a catalyst. What I want to talk about in this video are those first 2 options, changing the structure of the ester or changing the structure of the reducing agent. If we want to reduce esters because that's what we have in our synthesis, or that's what we can make, or that's what we can buy, then that option's also out. Typically, if we run into these kind of reactivity problems, we wouldn't be changing the compound that we're making the adjustment to. We would be changing the reagent, the thing that we can actually use and throw away, because it's kind of just a tool to adjust structure, right? There's a practical component here, which means that our consideration is going to be how can we make the BH4 anion, or something like it, more nucleophilic at hydrogen. Well, if we remember from the first video, we discussed that the boron is an inductive donor and that its donation ability is increased by the fact that the boron is negatively charged. Right? So we've got those 2 different features. One of them is just pure electronegativities. The other would be the fact that the B is negatively charged. If I want to make the hydrogens more nucleophilic, then I need to actually make the hydrogens more electron rich. As I make those hydrogens more electron rich, the negative charge that's developing on them is destabilized, and we get more reactivity as a nucleophile, right? So one way I could do this to make my hydrogens more electron rich is try to make this inductive donation stronger. So one strategy, increase inductive donation in terms of strength, right? So if we went from, let's say, boron as a weak inductive donor, for instance, maybe we would try to make some structural change here to make, boron or a replacement atom. It doesn't matter that we're using boron necessarily. What we do definitely need are those hydrogens. We try to make that a better donor group, right? So what I'd like for you to do is come up with a proposal, right? How would you change the structure of BH4 minus to actually make it more nucleophilic at hydrogen, right? So I just want to be clear, you can change boron, you can change it to other elements. Using the periodic table might be a great option for how you would solve this problem, but think creatively and use what you know about where induction comes from, for instance, to help guide you. So pause your video and make your proposal. One thing you might consider is that inductive donation comes from dipoles, or differences in electronegativity between 2 elements, right? So we decided that boron is an inductive donor to hydrogen because boron is a little bit less electronegative than hydrogen. And that means that a boron-hydrogen bond is polarized toward the hydrogen atom. If I want to make this inductive effect stronger, then perhaps I could actually make a larger difference in electronegativities between whatever atom is in the middle of my cluster, so for instance boron, and hydrogen. So let's look at some actual electronegativity numbers. So our electronegativity of hydrogen is just about 2.2. The electronegativity of boron is, let's say, 2.0. I'm going to round these numbers just a little bit. So we can see that here we've got a little bit of an inductive effect going on, a little bit of a difference. So this is going to be small induction, And if we look at the periodic table, I would probably, if I'm going to make a change to what, like the element that's in the center of this cluster, so boron, for instance, I'm going to choose something that has very similar bonding properties, right? So ideally something in the same column, because we know that there's a lot of conserved behavior there. And that means that I'm going to be looking at elements like aluminum, the element directly below boron. So the electronegativity of aluminum, we just based on where it is in the periodic table, we should assume it's going to be less than 2, because we know that electronegativity drops as I go down a column. And it turns out it's about 1.6. So now when I start to look at my electronegativity differences between hydrogen and aluminum, this is now getting pretty significant, right? Much more so than hydrogen versus boron, which means that aluminum is going to be a much more powerful inductive donor to hydrogen than boron is. So aluminum is stronger inductive donor. And that means that I can start to draw out at least a part of a reagent where I'm going to try to keep everything the same and just replace boron for aluminum. So I'll start with my aluminum atom. I'm going to put 4 hydrogens on. I know that if I do that the aluminum will also be formally negatively charged. It's going to have the same kind of bonding properties that boron does. So typically aluminum would form 3 bonds. If I form a 4th bond, the aluminum becomes negatively charged. Again, note there are no lone pairs here, just aluminum-hydrogen bonds. And finally, we know that, well, we're not just going to just get this anion. We're going to have to use some kind of a positively charged ion also. And that whole salt together would be the reagent. One option would be to use sodium, yeah? But it turns out that because of the solubility profile for these kinds of compounds, we actually need to use lithium instead. So we'll just use Li plus instead of Na. For the purposes of this class, that will not be an important distinction. Again, that's one of those like asterisk or caveat type statements. If you're an organic chemist or you're thinking you might become one, sodium versus lithium does make a big difference. Okay, but again, for our class, we're not going to worry over much about that particular effect. So this reagent here, we could write structurally. We could also write it out by using just the elements, so kind of a molecular formula. So lithium, and then aluminum, and then some hydrogens. So we could call this lithium aluminum hydride. That would be like the name you would use, and then we also can abbreviate this LAH, or La. So this reagent, La, lithium aluminum hydride, is quite a bit more nucleophilic at hydrogen than was the case for BH4-. And it's because of this design principle of adjusting the inductive capacity of this central atom here. So these hydrogens, for instance, I'll just box one. These are going to be much more nucleophilic than in BH4-. And that reagent, LAH, or lithium aluminum hydride, might allow us to be able to reduce actual esters. So if we actually do this kind of reaction, where we keep like the same generic structure, and all we'll do is change the nature of the reducing agent, or its structure rather, we find something different happens. So here's our ester. All right, lithium aluminum hydride. First of all, if we did this with an alcoholic solvent, we actually just start a giant fire. And that actually comes from the fact that while we're making these hydrogens more nucleophilic, we're also making them more basic. And if you present them with ROH, we actually deprotonate the solvent with H to make H2, which is flammable. And that reaction is so exothermic that a lot of times it will actually ignite. So this comes from mixing our LAH, or lithium aluminum hydride, with a protic solvent. This is pretty spectacular. These fires can be quite dangerous. I've actually seen a couple of them in my career, but they're also fairly attractive. Chemists usually like fire. Maybe that's the reason why we do what we do. Just saying. So I'm going to post a YouTube link in the description of this video for where you can go see what happens when you treat lithium aluminum hydride with an alcoholic solvent or water, for instance. All right, so we know right away that we can't do this by just mixing everything together. We're going to have to do this in phases. So an adjustment would be like, let's do the lithium aluminum hydride first. So we'll say 1, step 1. So we'll mix the ester and the lithium aluminum hydride, let that stir around, maybe go get a coffee or something like that, and then we'll come back, and then we'll do a workup, right? So rather than having our source of protons there right away when the reaction is going, we're actually going to like come back later and add water or some other weak acid to actually put a proton on the O- that's going to be developed. Think back to the mechanism of borohydride reduction in the previous video. And also to destroy any remaining reducing agent. So we'll just say a water workup. It's important to note that we're actually using Arabic numerals like 1 and 2 to denote that even though we're using a single flask, there's like 2 different operations that are separated in time from one another. And that means that most of the lithium aluminum hydride is gone by the time the water is actually being added. That's a safety thing. Otherwise, fire. But one more thing we have to consider, we actually don't make this product at all. We make an alcohol. So we'll get a compound that looks like this. And then if you're really keeping track, you'll also get an alcohol associated with this part of the ester. So plus. And just to make it a little bit clearer where things are coming from, so this group here is this group, and this group here is coming from the rest of the ester. So I noticed a few things. This just looks like this whole group functioned as a leaving group, yeah? Looks a little bit snack-like to me. This thing is coming off. And it also looks like if I look at my oxidation levels, I'm going from +3 all the way down to +1, where I've introduced these 2 hydrogens. So it looks like I'm doing some kind of a double reduction here. I mean, we've seen things like this before in the opposite direction, where we've done alcohol oxidations. We learned that the Jones oxidation goes from +1 to +3. It looks like lithium aluminum hydride is the same kind of a process, but now it's in the reducing direction, right? So in the next section of this video, we'll look at a mechanism for lithium aluminum hydride reduction, which looks very similar in some ways to borohydride. But we'll use that mechanism to explain why we get this double reduction process. If we look at this mechanism involving, we'll use a specific ester here, this is ethyl acetate, and the business end of lithium aluminum hydride, so this is just the part that actually is going to participate in the chemistry in a meaningful way for us, we can actually find out where this double reduction comes from. So to get started, we'll treat this the way we always treat any mechanistic problem. We have a nucleophilic species or part of the molecule, so that would be one of my hydrogens. I'm going to just choose one of them arbitrarily, so this would be my nucleophile, and then my electrophilic site is obviously going to be the carbonyl. You're going to hear me say that a lot all semester long. So again, we're going to have electrons that are building up between the aluminum and the hydrogen, and they're going to be close to the hydrogen because of the powerful inductive donating ability of this negatively charged aluminum atom. That means the electrons within this bond are going to be the ones that get transferred into a new bond between the hydrogen and the carbonyl-carbon, and that will break the carbonyl CO pi bond. So this looks like an addition, the first step of a snack reaction. And if I draw out the intermediate that would form, I should have something that looks like this, and I'm not going to worry about what happens to the rest of the aluminum-containing compound at this point. Same thing as what was true in the borohydride case. Those compounds are not innocent, but it's kind of complex to talk about what all ends up happening with them, and at the end of the day, they become waste. So rather than going into those details, I want to try to keep things a little bit cleaner. I'm just going to ignore the rest of the aluminum junk at this point. If I look at this structure, though, it reminds me of something that we talked about a lot in Unit 5, a tetrahedral intermediate. It looks like I've added a nucleophile to a carboxylic acid derivative, right? So here's our tetrahedral intermediate. And we know that tetrahedral intermediates undergo elimination. So the question would become, well, if I'm going to restore the carbonyl, which of my 3 attachments to this carbon, OET, H, or carbon in our methyl group, which of those is most likely to serve as a leaving group? And what you all told me in your homework for the SLO section, or the snack section, is that we could usually decide on leaving groups based on charge stabilization. So if I put a new lone pair on this oxygen, that's going to be way better, way more stable than putting it on hydrogen to run the reaction backwards, or especially to put it on carbon, right, which we know is typically unlikely. That means that this ethoxy group will serve as our leaving group, just kind of like we thought might happen based on the structures of the products we observed when we actually just ran the lithium aluminum hydride reduction initially. So I'm going to curve here. This looks like an elimination. And if I follow my arrows, it looks like I'm going to end up with a new carbonyl. The hydrogen's still attached, the methyl's still attached, and I have this OET minus now, so that's now left. If I look carefully at what's been done here, I started out in an ester where the carbonyl carbon is at the +3 oxidation level. And if I follow that carbon through the addition and then to the elimination, it looks to me like I'm at the +2 level. So this initial process is a snack reaction, and it's the first reduction that happens. So we can write that down. First reduction is a snack with H nucleophile. If you want to be very careful about our analysis, we would find that the addition part is the actual reduction, right? Because if I look at this carbon, where I've added the hydrogen, we're at the +2 level. So the elimination is redox neutral, but adding this hydrogen with the electrons, that's the important part. That's the actual reduction that's happening now. Okay, so why is it that we don't isolate the aldehyde? Let's write that down too. Our aldehyde is not isolated. It would be nice if we could actually do that, a single step reduction, so from +3 to +2, but we can't. It doesn't work that way. The reason why is a little bit, it's not obvious until maybe you hear about it and then you're like, oh yeah, of course. So let's imagine we're watching this reaction inside a flask. At the very beginning, right, like the instant that these compounds are mixed together, there is a lot of each of these, none of the tetrahedral intermediate, and none of these compounds either, right? But now let's actually just like press play for, I don't know, a fraction of a second. We're going to have a few of these molecules react. We'll maybe have an even smaller amount of the intermediate, and then we'll start making some of this aldehyde. Okay, so what that means is that we still have a lot of this, a lot of this, a little bit of this, and a little bit of this. Crucially, that means the aldehyde is forming in the presence of our reducing agent. Why is that important? Well, if I look at an ester versus an aldehyde, which of them do you think is more electrophilic? From SLO4, we know that like removing or missing this resonance donor group tells us the aldehyde is quite a bit more electrophilic than the ester. So if you're a nucleophilic hydrogen, who are you going to react faster with? The aldehyde or the ester? Right. So the idea here is that as soon as the aldehyde forms, this is now the most reactive carbonyl that's present, and that means the fastest reaction that can happen will be reduction of the aldehyde, not reduction of the ester. So our aldehyde is more electrophilic than the ester, and therefore will react faster with aluminum hydride than the ester. So as soon as a little bit of this aldehyde forms, it reacts again. And it's going to react with another equivalent of AlH4 minus. So I'll draw that over here. My hydrogen's in. And so here we would do the same thing again. Nucleophilic hydrogen, electrophilic carbonyl carbon. That will do an addition. And if I follow my arrows, my methyl group and this hydrogen are not changing. The oxygen is still in the molecule, but only bonded once to the carbon. It will become negatively charged. And now I will have two hydrogens attached to this carbon, and if I follow the oxidation level, it looks like I'm going down another level, so from +2 to +1. So this second addition is the second reduction. At this point, the reaction stops. There's nothing really that can be done to this single CO bond until the workup. So we'll stop here until the workup. Once the workup happens, let's say I add some water to this very carefully and slowly and at low temperature. We have a proton transfer where this basic O- can remove a proton from the water molecule. That gives rise to our alcohol. And it will also give rise to hydroxide, the conjugate base of water. So this reaction is reversible. We're going to use the same logic we used when we talked about the use of a solvent as a proton source in the borohydride reduction. We're going to use a lot of water. So like thousands or millions of molecules of water for every molecule that looks like this. The other thing that I'll note is that this compound, OAT-, which was our leaving group after the elimination, it's just been following along, and it will also remove protons from that huge excess of water to form an alcohol as well. Sorry. There we go. Cool. So this part would be from original leaving group. Okay, so this is a lot, right? There's a few keys that I want to make sure that you take away from this. The first one is here, right? Our first reduction, you already know how this works. It's a snack reaction. We've just specified a nucleophile, something that's going to be a hydrogen nucleophile. And this other idea is also really important. We're going to see it again and again and again throughout the rest of the semester, that if you do these reactions, especially with things like carboxylic acid derivatives, the products that you make initially are often going to be more reactive than where you started. And so it's very difficult to stop. We'll see that exact same phenomenon with other kinds of reactions. So rather than just memorizing, like this is how LAH works, I'd strongly encourage you to make sure that you understand this kind of idea. I'll be invoking it again in multiple units going forward. Okay, so now that we have the mechanism of lithium aluminum hydride reduction, let's look at some practice problems where we're going to predict the structures of what might form if we actually treat carbonyl-containing compounds with this basically nuclear weapon of reducing agents, right? It's so reactive. Let's look at 3 different reactions, all involving lithium aluminum hydride as a reducing agent toward different kinds of carbonyls. So in all of these problems, we'll assume that there are excesses of both lithium aluminum hydride and, of course, the water workup, which would be typical for a workup reaction. What we know is that as long as there's a sufficient amount of lithium aluminum hydride around, it will cleanly always do a double reduction of esters, for instance. So we know we're going to double reduce. And that means, spelling mistake, better, that we're going to keep the rest of this molecule the same. So aromatic rings and alkyl halides, for the most part, aren't affected by lithium aluminum hydride. Again, there are counterexamples to that point that would be more relevant if you're thinking about a career in organic synthesis. We would end up with a primary alcohol. So our pattern here is ester to primary alcohol. Usually we don't care too much about what happens to this part of the ester. A lot of times it's like a methyl or an ethyl ester, and we're not interested in that part of the compound. What we want is the part that has the carbonyl that was a part of the original structure here. So if you felt like being really thorough, you could also write MEOH, right? So the leaving group from the initial snack and then proton from the workup. But really, if you left out the methanol, that's okay. Right, I wouldn't be worried about that. We could also look at a case where we have a ketone and an ester in the same molecule. So again, we'll assume that there's a large excess of lithium aluminum hydride, which means that every functional group that can be reduced will be reduced. What I'd like for you to do in that situation is predict the structure of the final product after all of the reductions that you think are viable have happened and the workup has occurred. So pause your video and predict the structure of the product for this reaction now. We know that esters react with lithium aluminum hydride with no issues, right? So reasonable rates, and that means that ketones, which are even more electrophilic than the esters, they should also react. Remember that the reason that borohydride didn't react with an ester was because the borohydride wasn't nucleophilic enough. Well, we know that this hydrogen is definitely nucleophilic enough to react with this weak electrophile. If you give it a better electrophile, it's probably also going to react there as well. And that means that I'm going to adjust a few different oxidation levels. This carbon, the ketone, starts out at +2, whereas the one of the ester starts out at +3, and that means that I'm going to do a double reduction here, so from +3 to +1, and a single reduction from +2 to +1. So one way to think about this is that lithium aluminum hydride will adjust everything to the +1 oxidation level if it's a carbonyl, and then that's it. It doesn't go any further than that. So we have our secondary alcohol from our ketone. So that looks just like a borohydride reduction, and that way those are interchangeable. And here we're going to go to another primary alcohol, so ester to primary alcohol. And I'm going to draw in all of the hydrogens that were delivered from the lithium aluminum hydride reagent. So we're actually doing 3 separate reductions, 2 at this carbon and 1 here. So my final oxidation levels, +1, +1. Finally, we could look at a compound that looks like this. So like an isolated alkene, for instance, rather than one in an aromatic ring, and an aldehyde. So what we find here is that alkenes tend not to react with lithium aluminum hydride. They tend to be inert. They don't get reduced. We already saw in our conversation about the mechanism that aldehydes absolutely are reduced. So this aldehyde starts at +2. And rather than saying, oh, well, I'm always going to do two reductions with lithium aluminum hydride, better to think about things being reduced to the +1 level. In that case, I'm only going down 1 level. Yeah, +1 is my floor. Now, everything else in the structure will stay the same. So here I've got my alkene, my hydrocarbon framework, and here with these like longer alkyl chains, it's important not to add or drop carbons. So I'm actually going to number from the carbonyl, so 1, 2, 3, 4 to that alkene, and that'll make sure that when I actually adjust what the aldehyde looks like, I'm not dropping carbons or adding them. So I'll work back the other direction here, 4, 3, 2, 1. That means that my oxygen is still attached to carbon 1. It will become an alcohol. One of the hydrogens was already there as part of the aldehyde, and then the other will come from the reducing agent, the lithium aluminum hydride. So we're going from +2 to +1. And just like we had ketone to a secondary alcohol, we'll have an aldehyde to a primary alcohol. Okay, so lithium aluminum hydride in some ways looks just like borohydride. It's just more reactive, and it will reduce other kinds of functional groups, like, for instance, esters. The new part about lithium aluminum hydride was also that it's capable of doing these double reductions so long as you start at the C +3, or even, I guess, the +4 oxidation level. You'll always drop down to the +1 level and then stop. So in the last section of this video, we'll look at a couple of other interesting reactions that lithium aluminum hydride does that don't necessarily follow the patterns that we've been developing so far, but do involve carbonyls. Lithium aluminum hydride can also reduce functional groups like amides, which have carbonyls but don't have the same kinds of oxygen substituents that maybe an ester would. We also know that amides are very, very poor electrophiles relative to other kinds of carbonyls that we've seen. So there might be kind of a question, well, does this reaction work? So here's our poor electrophilic site. The answer is yes, right? So I alluded to earlier that lithium aluminum hydride is kind of like the nuclear weapon of reducing agents. It's so reactive, it has no issues reducing even carbonyls like amides, for instance. But this reduction looks a little bit unusual in the sense that you would do a snack initially. So you would reduce this carbonyl to like a CO single bond with an O minus, like the tetrahedral intermediate kind of a thing, right? And then you might expect, well, okay, I'll lose this group because that would be my leaving group for a snack. But that turns out not to be what happens. These reactions proceed through a different kind of a process where this oxygen is lost entirely, and we end up making amines instead of aldehydes or primary alcohols. So we end up forming compounds that look like this, where the two hydrogens I've drawn explicitly here, those are coming from the reducing agent. Again, you could use isotopes to figure this out. So if we actually follow oxidation level of the carbonyl, it's +3 in the reactants in the amide, and that same carbon is here +1. So we're doing a double reduction, but what's different is that we're not actually doing a snack anymore, or at least nothing that looks like a snack exactly. To my knowledge, the mechanism for these amide reductions of lithium aluminum hydride is not necessarily well understood. So I'm not going to try to like come up with some argument for why this would be. I think it's quite surprising, but it's reliable. This is essentially always how amides undergo reduction with lithium aluminum hydride. The other thing I want to bring up is what happens when we take functional groups called nitriles, which are CN triple bonds. Those can also be reduced. So these are not necessarily carbonyls, but nitriles have a lot of similar behaviors to carbonyls because of the fact that we've got this pi bond that's highly polarized toward the nitrogen. Yeah, and that means that the carbon of the nitrile is electrophilic. So a nitrile carbon, specifically the one that I'm showing here, is about as electrophilic as an ester. Maybe a little bit less, but certainly a lot more reactive, a lot more electrophilic than an amide carbonyl would be. Because really there's no resonance donor here, yeah? You're not necessarily polarized as much as you would be in a carbonyl because the nitrogen's not as electronegative as oxygen, but you don't have these substituent effects that can help pump electron density back in, right? And so this is kind of generally what we see. In these kinds of cases, you might expect the hydrogens from lithium aluminum hydride to serve as nucleophiles toward our electrophilic center, yeah? And that's exactly what happens. But again, if we actually look at our oxidation level, we're at +3 for that carbon, and therefore we should expect to get to the +1 level with lithium aluminum hydride. That's exactly what happens. So most of the rest of this molecule will stay unchanged. We'll introduce 2 different hydrogens to the nitrile carbon center. That's the 2 different reductions. And then after the workup, we'll end up with a primary amine. So we've got a nitrile to primary amine. And here we've got an amide, in this case a secondary amide, to a secondary amine. So if we had done this with a primary amide, you would make a primary amine, and a tertiary amide would become a tertiary amine. Another way of saying that, rather than memorizing all the permutations, is all we're doing is adjusting the carbonyl. Everything else in the structure is a spectator. So if I have 2 different carbon groups attached to the nitrogen, I'm going to have 2 different carbon groups attached at the end. If I've got 3 different carbon groups, I'm going to have 3 different carbon groups at the end, right? So rather than, again, don't memorize all the permutations, there are patterns here that are way easier to use. I'm going to treat both of these reactions for us as mechanismless. So it's important to know what the final products are. We can reliably say for sure that these hydrogens are acting as nucleophiles toward electrophilic centers, but the nature of the intermediate structures and how we're getting second reductions, for instance, in some cases are murky or not really well understood at all, so I don't really want to belabor that point. There are other permutations as well that we haven't talked about in this video. For instance, like what happens when you take a carboxylic acid and treat it with lithium aluminum hydride, or an acid chloride, or an anhydride. Those are good exercises for you to think through because you understand how these reactions work, and you understand what types of structures are involved, and you can look at those structures to assess reactivity. So to help you do that, and to help you sort through all of the permutations that exist in this section, I'm going to post a table to Brightspace, which basically lays out our different common carbonyl-containing functional groups, so things like esters or amides, ketones, aldehydes, all that good stuff. And both sodium borohydride and lithium aluminum hydride, as well as reagents we'll learn about later on in the unit. So you have like a place, like a single page that serves as reference, so you know what all of these different reactions look like between different carbonyl functional groups and different kind of reducing agents. So I'd strongly encourage you at this point, after you've watched this first 2 videos, to fill out both the borohydride and the lithium aluminum hydride parts of your chart. You're welcome to work with this together on this together. You're not going to turn the chart in for points, but it is helpful. You'll be able to use it on the final exam, for instance. And of course, it's also a good conversation starter. So you can talk to each other about it. You can ask me about it on the discussion boards, or you can come to office hours. Any of those will be options. But again, strongly recommend working out that chart. So that's the end of our video dealing with lithium aluminum hydride. Just to recap, the idea here is like the reagent behaves a lot like sodium borohydride does, but it's just much more reactive because the aluminum in LAH is such a powerful inductive donor relative to, say, a boron atom. So those are the two hydride reduction reactions we'll learn about. Moving forward, we're going to be talking about forming new carbon-carbon bonds by reducing carbonyls.